Right, so mid-chapter 8 is really only 2 sections, but it's huge, right? 8.3 and 8.4 have so many concepts to them. That's what made this chapter, this mid-chapter 8, feel so overwhelming. First thing we talked about was making sure you know what it means to factor. That means look for a GCF. That means factor a trinomial, maybe. I can spell. Right, that's like where you made the X and figured out like what worked, right? Factoring. And then restrictions, this keyword here refers to values that the X can't be. Bad values or like restrictions on the domain, right? Then we talked about discontinuity. Points of discontinuity are what you have to restrict from the domain. You have to say those values cannot be in the domain. There's 2 different kinds of those, right? Removable and non-removable. So we talked about that too. Just kidding. This is Hunter. Then, after we do the asymptotes, you got to know what it means to find x and y intercepts, and you don't need the calculator for any of this stuff. Same thing with the rules for horizontal. In my notes, we had a box where we wrote the rules in them. The last thing is how to use the calculator as a tool. We did a big table. We talked about how to see what it looks like and understanding which way the graph is traveling. So we can do that last. First things first, I want everyone to write this down. If you have a piece of paper and a pencil, let's start with a problem like number 1. This is y equals 5x over x minus 4. Find the domain and state any restrictions. So the first thing to check is there anything I have to do to factor this? No, both the numerator and denominator are linear, right? So because there's no factoring to do, I'm going to check to see can anything cancel. Does anything cancel out? No, which means there's no what? Gianna, yes, there are no holes, no removable points, no holes. Brooke, why can't I just cancel x's like this? Why can't I do that? Those aren't monomials. Had there been another x on the outside, well, then I could cancel those x's, but like I'd be breaking up a binomial family. I can't do that. You can't just take a piece of a binomial out. It would have to be an entire. Correct. And reducing is by division. So because I can't cancel, it means there's no removable points, no holes. Well, that means then the one problem in the denominator creates a what? Correct. There is one vertical asymptote, and it's at x equals positive 4. Right, Mandy, you were saying that earlier. You felt like that was the easy part, just flip the sign of the number, right? It comes from taking x minus 4 and setting it equal to 0. Like that's where it comes from, but we all know the shortcut of just flipping the sign. Okay, so wait, what were the restrictions on the domain? Right, now Gianna just said domain can't be equal to 4. You can write it like a sentence. You can do an interval, negative infinity to infinity, where x cannot be 4. And in my class, we use a symbol for that. It's a capital R with a line through it. It just means the set of real numbers, but you have to say what x can't be. All of these are acceptable ways of saying what the domain is. They all kind of mean the same thing, right? Restrictions on the domain are bad values. It would make, it would make me do something not allowed. What am I not allowed to do in algebra? Divide by 0, right? Or square root a negative. It doesn't produce real numbers. So that's why those are considered restrictions. Okay, next. Can we find the intercepts? How do I find the x-intercept? There's a shortcut for it. X-intercept is found by setting the numerator equal to 0. So I would be like, okay, 5x is my numerator, set that equal to 0, x equals 0. So x-intercept is 0, 0. Now finding the y-intercept, you have to do something else. What was the rule for that? Plug in 0 for x and simplify whatever's left over, right? So my trick, this is what I love about y-intercept. Imagine the x's disappearing. Because if you plug zeros in for them, aren't they just gone anyway? What do I have left if that stuff is gone? I have 0 over -4, which would be simplified down to a 0. So my y-intercept is also 0, 0. Let me just show you something really quick. Let's just say hypothetically that this was 5x minus 1 originally. Like I just put that in green, right? Had that actually been minus 1 up there, what do I get now when I make the x's go away? It would be 0, 1/4, right? So it depends on what's up there. Now, I just made that up, so I'm going to take it back. But those rules make sense? See how this is a lot to remember? It's like little rules, little things that you have to remember. What else did we do from the beginning? Restrictions on the domain, points of discontinuity, no holes because nothing canceled, x and y intercepts. Can we sketch what this might look like without a calculator? Well, I'd have this little coordinate plane, right? What are the things I know just from my rules? Okay, so I know I have a point here, a good point, right? Now I know I have a bad value. Where does that? And so what do I have to put there? A dot? A hole. A wall, exactly. A dotted line, which is a horizontal or a vertical line at x equals 4. All right. I know one more thing we can do. We can figure out the horizontal asymptote, if there even is one. What's the rule for horizontal asymptotes? Mhm. That's right. It has to do with the degrees. Find the degree of the numerator and denominator and compare them. Then there's rules attached to that, right? So here, degree is 1. Here, degree is 1. So what's the rule when the degrees are the same? That, leading coefficients. 5 over 1. So it's just 5. So the horizontal asymptote is going to be y equals 5 over 1, which is y equals 5. Okay, that's like a floor, right? Or whatever we called it a minute ago. 1, 2, 3, 4, 5 is here. Can you visualize what this is going to look like? You know you have one dot at the origin. I know Mrs. Shaw's classes were saying that you could just sketch it. If you know you have one good point down here, it's going to be like this. That means the other piece is here, right? Well, rational functions look like this. In my class, I would have gone to the calculator and said, don't guess. Let's see what it looks like. Let's make a table so we have 3 points on the left and 3 points on the right to see where they go. So I'd be like, well, let's go here. Correct. So because this is also for my classes, I'm going to go ahead and continue this. If you're watching the video, type this in your y equals screen and see what it looks like. We always make a stacked fraction to see exactly what's given on the page. Here it was the green writing. And then we hit the graph button to see what it looks like. There it is. How do I know? I know. How did I know that? Well, you have to know what these dotted lines actually are. What are they called again? What do asymptotes do? When you say they can't go further than them, we mean the curves will be approaching them without ever really reaching them. So I knew the only way that this would make sense is if I had something over here that's approaching each of these asymptotes. I knew that because that's the definition of an asymptote, right? It's a place where all the values start to get closer and closer and closer on both sides. And then I knew that this side was a reflection of that. This problem had one vertical asymptote. Remember the one on the review, we were looking at practice tests, there were two? Because there were two factors in the bottom that didn't cancel, where I just highlighted. If there's two factors down here, then there's two vertical asymptotes. Gianna? Did she talk about that with testing limits in class? because I didn't teach it that way. You can plug numbers in to test the limit to see like where the points actually are going. But in my class, I was like, let's look at the table. And so I was like, well, second graph would take us here. Here's my error. That's my asymptote, right? Correct. I'll tell you what I told my class too. That's correct. That's the now. Can you remember that? Because that's like a tricky trick. Like it's weird, right? The answer is that only horizontal asymptotes can never be crossed and only once. And what does that look like? And why is that even happening, right? On my practice test, and I don't know if yours is the same, we had one like that we finished right as the bell was ringing today. This is what this last problem in my review looked like. Nothing canceled, so there were no holes. There was one asymptote, but it was 3, right? From that denominator, it's x equals positive 3, so it was a vertical line at 3. The degrees larger on the bottom, which means what was the horizontal asymptote? See the degrees larger on the bottom? What was the rule? 0. But then when you go to find the intercepts, you realize that the x and y intercepts are at the origin. How could the graph intersect at the origin if that's right on top of the horizontal asymptote? That's supposed to be a bad value spot, right? Like a place where it's not going to cross. Well, that rule only applies technically to vertical asymptotes. The horizontal can be crossed once. Now, I'll show you dramatically what's actually happening here. Over here on the right, the curve is pretty spread out and it's above and to the right only. It's like over here in this first quadrant spot, right? But what happens on the left is really interesting. It's actually high over here, bumps down, and then starts approaching from the bottom side, and it hugs the floor from the bottom side. It doesn't go that low. It's actually like not that deep. But I showed my class that to be overly dramatic to show what's happening. And that's what happens with the horizontal asymptote sometimes. It means something in engineering. It's actually very cool, but like it's a lot of information for algebra too, you know? Mm-hmm. Mm-hmm.
That had a double, it would be -4.
Mm-hmm.
Or a +4. Where do you put that?
So let's do one like that next. First of all, did we make a little table? If you're watching the video, in my class we made tables and you'd have a little T-chart given to you where you had to like make this, right? So I hope you did that at home. If you were practicing this problem, you'd see the other part was over here somewhere. Now, the problem Brooke is asking about is what happens and what does it look like when you have a hole. So let's find one like that. Here we go. This one's going to give me a hole. Y equals, go ahead and write this down, x plus 8 over x squared minus 64. Directions will say, make a graph, find the points of discontinuity, find all the things. The directions are like a paragraph, right? It's a lot. You think?
Yeah, because like you know that something's going to cancel.
Why? How did you know that before you're doing it? Yeah, she's seeing that this is a perfect square, and so, well, it's a difference of squares, which means on the bottom I'm going to have x plus 8, x minus 8. And that's fantastic, because what happens? It's a 1 on the top. Now, the x plus 8s are gone. I have removed them, which means what? There is a hole at x equals -8. So if I go to make a table, which I will in a minute, and I use -8 as one of my values, what am I going to see on the y side? Error. Error, because it's a bad value. There's no output for it. It's not going to have a good, there's no way to graph that. It's a hole. It's an open circle. Okay, wait. If there's a hole at -8, what do I have to do with this? The one that didn't remove, the non-removable. Yeah, vertical asymptote, which is the wall at x equals +8. All right, I'm starting to get a little visual now, right? I'm starting to see in my mind's eye before I even go. 1, 2, 3, 4, 5, 6, 7, 8. I'm gonna have a wall here. Is there a horizontal asymptote? And if so, what is it? It is. Go back to the original problem and compare the degrees. Degree is 1, degree is 2. When it's larger on the bottom, what is it automatically going to be? Good. So horizontal asymptote is automatically at y equals 0. So I'm going to go ahead and sketch that too. There we go. Now I should figure out if there's any intercepts, because that would give me like a visual of like where's my graph going to be? Is it going to be like this way? I mean, I don't know anything yet. Is it going to be this way? How am I supposed to know? The intercepts will help. So let's figure out what is, if there is one, an x-intercept. What are you doing? What's the rule? Use the numerator. But wait, the numerator canceled. So x plus 8 equals 0, x equals -8 can't be an intercept, it's a whole. It's not, it's a bad value. This is not an intercept, it's like an open hole. No, it's nothing. You would say there isn't an x-intercept. That would be like the answer you'd write if there was that list of things you have to find, right? What about the y-intercept? What's the rule for that again? Yeah. Yeah. Right. I'm like getting rid of these, right? It's 8 over -64. And when I reduce that, my y-intercept is 0, comma, what was it? -1/8? Where is that? Where's that on the y-axis? Like barely, right? -1/8 would be like barely right here. Ah, so now I have a little visual, a little clue, an intercept. That means I have a curve down here because it has to hug those walls or the floor in the wall, whatever you want to call it. It has to. That's like what this looks like. That's what happens when you plug a whole bunch of values in for x to find the respective y's. It approaches the vertical asymptote. And then the other piece is going to be up here. Now, I will say this though. If I'm going to be specific and I'm going to graph my hole, what did we say the value for the hole was again? So at -1, 2, 3, 4, 5, 6, 7, 8, I need to have an open space like this. There's my hole. There it is. At -8. Well, it's part of the graph. I mean, it's a space where the graph jumps, you know, it's not included. You're right. So you know what I did is I counted on the x-axis till I got to -8 and then kind of went down to where my curve would be. And I included that as a missing value. All right, so you know what we can do now, and I do this in my class, of course, is I go to my calculator and I type this in. So the problem was, as my little stacked fraction, x plus 8 over x squared minus 64. Is that right? Does it match what I drew? What's happening over here at +8 where my blue curves are? What's happening? Like right here, what's happening here? It's a wall. The curves are approaching but never reaching that wall, yes. Now, if I go to my table, I want to go, I want to go see, first of all, is there an error at -8? Yes, I said a hole was going to be there. And then I need to go to +8. That's my asymptote, so I should see error there too. And then you have to make a big old table. I mean, mine will say that. Plot points on the table, plot them on the pictures, connect with a smooth curve. You have to do that. So your little t-chart, you're going to include some values here that you see. Now, if it says to graph all points of discontinuity, you have to graph the hole too. If you found that hole, don't just like haphazardly draw the sketch and not include the hole if the directions say you have to. My test is like that. It'll say graph the points of discontinuity, so you have to. You have to graph the hole, you have to graph the asymptotes. Does all this stuff make sense so far? Do we feel good about... Good, yeah. Do you feel good about the way it progresses? Factor first, find holes if there are any. Do vertical asymptotes next. Then maybe draw a little sketch where you draw the dotted lines in because you know they have to be there. Yeah. Anything else about graphing though? We kind of hit all the basics, but was there anything else about graphing? Because I'd like to do some of those that you're talking about now. Okay, so let's look at a couple of those. The directions will say simplify and state any restrictions on the domain. So I like to make up. I would be able to find one. I don't know if I can. Let me just make it up then. Let's say the problem said, as a fraction, x squared minus x minus 12 over x plus 1. This is what you meant, right? Two fractions like multiplied together? Okay. And then let's say it was x squared minus 1. And then let's say we have x minus 4. Directions are to simplify and state any restrictions on the domain. How do we start? Absolutely. You have to start by factoring. Okay, so in the numerator, the first numerator, I'm thinking what two numbers multiply to negative 12 so that they add to negative 1? Okay, so x minus 4, x plus 3. In Algebra 1, we made the x, didn't we? And we would put the negative 12 at the top and the negative 1. It's fine, no shame in that. You can still make the x if you want to make it visual. The first denominator is already linear, so I'm just going to rewrite x plus 1. What's going on in the second numerator? Linear, it means x is to the first power already. I can't break it down any further. What about this second numerator right here? That's right. This is called difference of squares, x plus 1, x minus 1. And then my last denominator, x minus 4, I'm just going to write that again. Now what? Cancel stuff. Remove stuff that can be removed. I see x plus 1s. I see x minus 4s. When they're not exactly the same. Like if this right here had been x plus 2, then I can't do it. Or like if this had been x plus 4, I can't cancel it with an x minus 4. Anything else I can do? Well, no, I just have to write down the two things that are left. And what's my denominator? A 1. So I don't even need my fraction bar. I'm finished when I get to here, but I have to state what the domain is with restrictions, right? So I would say my domain is really everything except what bad values. Right. Now, where did you get those from? In the original problem. The original problem. I mean, I could have looked here too, the factored version of my original, but like you have to find those bad values before you start canceling stuff and like lose it, right? Don't lose something in the middle of your work. Why did I not have to consider all three parts of the fraction when we talked about this before and we did have to? Why? Correct. Correct. This was a multiplication problem, which you don't flip anything, right? Had this been a division sign, I would have to do the keep, change, flip thing, and I would be flipping the second fraction, which creates another problem. So this domain answer is also part of my final answer because it lists what x can't be. In my class today, somebody was like stressing out about knowing were these holes or asymptotes. Do I have to say that? Why are we not doing that? I said, don't worry about it. Didn't ask for it. All it said was state restrictions. Well, that's this and this. It doesn't matter what kind they are, not this time, right? So just figure out the bad values and list them as x can't be that. Right, exactly. Let's try one with division. And this was throwing my class today too. Ones with monomials. You guys know what monomials are? Yeah, like no plus or minus signs. It was like stressing them out. So this is 2x cubed over x times x minus 3, then a division sign. And I'm going to go ahead and make this, I guess we could use some y's. Let's say 15y over 5, and let's do another x minus 3. Okay, so first things first. I notice it's a division problem. So when I'm considering what x and y can't be, I have to consider all three parts of the fractions like this. The only thing that I don't have to worry about is the first numerator, right? So in looking at this, I should consider, can I factor anything? Can anything be pulled out? No, I don't need to factor anything, right? There's nothing to do. So I can go to my keep, change, flip step. Change means make that a times and then flip the second fraction like this. All right, can I cancel some stuff? Yep, those binomials are easy to find, aren't they? You know what else I can do? The 5 and the 15, because they're monomials, I'm not breaking up a binomial family or anything, right? I'm not like subtracting 5 to cancel. I'm reducing by division. But what's left in the bottom with that 15? A 3. Can I reduce with a 2? I can't reduce with the 2, but I can reduce the x's. The big 2, the coefficient 2, cannot be reduced with anything. But x to the third, well, that can be reduced with one of these x's down here, right? Doesn't that leave me with x squared? Can I cancel that little y? No, there's no y's anywhere else. I can't, can I? All right, so let's see what I have left. I have a big 2. I have an x squared. I have nothing else over on the right in the numerator. And then what's left in the bottom? A 3 and a y. This is my simplified answer, but what is it that x can't be? And y? Can't be 3 or 0 because of this right here. This guy, that monomial, is a problem too, right? 0 is a bad value. 3 is a bad value. What else? Right, y has a problem too. Y can't be 0. That came from this part. This y, whether it was here or here, it was in the denominator at some point, so it has to be considered as a restriction. So this would be my final answer with my restricted values. Anything else from the practice test or review that stood out to you from the first page, like 1 through 6? I know. Anything with factoring or like, I don't know, my class was pretty good with the first page once we got through them. Oh, I remember what I was mentioned was, do you guys know what makes a function rational? Like if I gave you a whole bunch of functions. No, that's something else. Here's a bunch of functions, and I want you to tell me which one is called a rational function. Okay, so here's one. Here's another one. Here's another one. And here's one. And here's one. You know what's crazy is you guys have seen all these before. These are all functions you have seen and graphed before. I'm using a lot of 6s. I don't really know what my issue is right now with the number 6. Something else. Only one of these that's called rational. No. Nope. It's this one right here. This is the rational function. What makes something a rational function? Mandy's remembering the definition. It was written as a function that's p of x over q of x. It means you have an x in the denominator somewhere. You've got a polynomial and a polynomial inside a fraction, numerator, denominator. You're creating a fraction with a variable in it, yes. Yes. Now, the other ones, the other ones are like not a problem. These are all things you've done before. You may not remember them all well, but the first one makes a straight line. It's called linear. That was chapters 1, 2, and 3. The second one is called quadratic. What shape does that make? Parabolas. We did that in chapter 4. Then we did a beautiful chapter 5. I loved it, with all the curvy ones with the maximum, minimum values and all the fun stuff. That's where we did ones like the third one. This is called cubic. It makes a curve like this. And the last one, which is called quartic, that has like more turns to it. We also did quintic, which is to the 5th power. But what were these? Exponential, logarithmic. This was chapter 7. Exponential was when you had like a flat side and a really high side, and the log was like a reflection of that. It was the inverse of that. A flat side with another like tall side. This highlighted bit is what we're doing in chapter 8. You need to know that for your test, by the way. A rational function has an x in the denominator. It's defined as p of x over q of x where they're polynomials. Anything else from this maybe? Good job. I can help you with some other things too, but I'm gonna turn this off. Good job.